This is the first in what will likely be 4 screencasts from Chapter 4. Hopefully you recall from first year chemistry some of your stoichiometry. The word stoichiometry, stoich right there, comes from the Greek word meaning element, and then metry, of course, means to measure. So we are measuring the amount of elements or atoms that we have to start with, and then what we have after we react them together. This is also a quantitative analysis, which means we're looking for quantities, which means we've got to be able to measure these amounts using various devices and scales and graduated cylinders and other mechanical contraptions. This yields information, and of course science is all about creating information, but you're creating information as you discover information that is already present in the creation. For example, we didn't make oxygen and hydrogen to react in a certain stoichiometric ratio of 2:1 with hydrogen and oxygen to make water. We discovered that information was already present in a breakdown of the water molecule into its constituent elements of hydrogen and oxygen. So where does this original information go, or come from, I should say, that we discover as we do science in any aspect of the entire universe? And of course, all of that information begins in the mind of the Creator. John 1:1, in the beginning was the Word, capital W-O-R-D, which is our translation of the Greek word logos, which means knowledge, rational mind, logic, the logos. And so that Jesus is the source of all of this original information that is embedded in creation. And then because he created us in his image, we are also rational and creative beings, as well as being spiritual and relational beings, like relational referring to the Trinity. Because of that, we also create knowledge using the knowledge that is already there. So that's a big picture idea of what we're doing. Science, of course, would not be possible if the universe was not rational, and if the universe in the first place didn't exist at all, but was just a dream or an idea or imaginary. And of course, science would not be possible if there were not patterns and regularities that we could discover and describe using laws and analogies and proportionalities. So keep all of that in mind behind this chapter. So this particular chemical reaction you're looking at forms a glimpse into what we often enjoy on July 4th, chemistry of pyrotechnics, where we create explosions, we create combustion reactions, oftentimes with many, many different colors, based upon which salts we put into the mixture. And you can read about fireworks. There's a lot of chemistry that goes into these fireworks, but a couple of fine points. Number one of the fine points is fireworks and often involve finely, sorry for the pun, powdered metals. Powdered metals mean you have a tremendous amount of surface area around each grain, each minuscule piece of powder. And as a result, you can bring lots of oxygen in the air into contact with that metal. Powdered metals are extremely explosive, and we have to store those in their own separate location in our chemical storage room. Sometimes, if we want to increase the rapidity with which the fine powdered metals react, we provide an oxidizing agent, such as potassium chlorate with those 3 oxygen atoms in that salt. And then there will be a binder that'll hold the metals and the potassium chlorate oxidizing agent together. And of course, in the process of doing these reactions, we have a redox reaction, as was discussed in chapter 3. So something is going to be oxidized and something is going to be reduced. And that means you're going to have an oxidizing agent and a reducing agent. And that reducing agent, if you think about what reduction is, reduction means to gain electrons so that you become more negative in your oxidation number. Well, in order to gain electrons, something in the reaction has to provide those electrons. That's the reducing agent. And what better reducing agents would there be but metals, for example, that have those extra electrons in their outer shell? You also get a tremendous amount of energy, and that energy can be harnessed. And when we harness this energy and generate enough heat, we can actually melt the metals so that when they form some type of amalgam and then cool and harden, you have what we call a weld, which is a way of putting these two metals together into one and make a very, very solid joint. All right. So again, this is going to be a quantitative study as opposed to a qualitative study. Qualitative study is what we kind of looked at in chapter 3. We looked at the quality of the reactants and the quality of the products. What colors were they? Were they solid? Were they liquid? Were they gas? Did they dissolve in water? Those are some of the qualitative aspects of a chemical reaction. This time we're going to put numbers to it, and the numbers are pretty easy. You're either multiplying and dividing by whole numbers, or you are multiplying and dividing by molar masses. And it's very simple kinds of math here. So if we look at this first example, on the microscopic scale, the stoichiometric coefficients in the equation refer to atoms and molecules or formula units. For example, I could say I've got 4 atoms of phosphorus that form 1 molecule of phosphorus in a tetraatomic compound. It's actually a pure element. And we have 6 molecules of diatomic chlorine. And we're going to get 4 polar covalently bonded phosphorus trichloride particles, molecules. And there are no formula units here because we use formula units to refer to ionic compounds, because ionic compounds are patterns of positive and negative ions in a matrix, in a geometrical array, in a predictable pattern. So we use formula units for ionic compounds, molecules for covalent, both pure and polar covalent compounds, and then atoms for elemental quantities. And so we would say that the stoichiometric ratio in this reaction is a 1 to 6 to 4 ratio. It's a 1 to 6 ratio as far as the reactants are concerned. It's a 1 to 4 ratio as far as phosphorus to phosphorus trichloride is concerned. And it is a 3 to 2, reducing to 6 to 4, a 3 to 2 ratio in terms of the reactant chlorine gas and the product phosphorus trichloride. Now, if we put some masses to this, for example, 124 grams of phosphorus and 425 grams of chlorine, we're going to get 549 grams of liquid phosphorus trichloride. And you can see that the 124 plus the 425 equal the 549. Atoms are neither created nor destroyed, and of course mass is neither created nor destroyed in a chemical reaction. Now, of course, you're going to have the same stoichiometric ratio whether or not you have these quantities of reactants and products. So you can have any multiple or factor of these quantities, and you'll get the same ratio. So, for example, we could cut them all in half or multiply all of them by 2, or cut them all in 10 or multiply them all by 10. Doesn't matter. Obviously, it's more common that you're going to mix up a bunch of reactants together, and they won't necessarily begin in the 1:6 ratio in terms of your starting quantities, but they will react in a 1:6 quantity molar ratio when they react, which means you might have some phosphorus, if that's in excess, left over, or you might have some chlorine gas in excess, if that is left over. And we'll be talking about limiting reactants, if you remember that term, in a few minutes. Also, a lot of reactions take place spontaneously. That means that they produce generally more energy than they than it takes to get them to react. They will end up at a more stable place. The products will be more stable than will the reactants be. That would be spontaneous. Spontaneous is not necessarily a reference to something that happens quickly. You can have rusting take place in the desert spontaneously, and it might take decades in the desert before a piece of iron oxidizes completely into rust. A combustion reaction would be a very, very rapid but spontaneous reaction. Spontaneous reaction basically means, in a sense, it goes downhill on its own, even though sometimes you have to give it a little push to get it started. And of course, that's a whole nother chapter when we talk about reactivity. Now, when we do stoichiometric reactions, step number one, as you can see here, is to write the balanced equation. And you remember each compound has to have the correct formula. So you need to remember how to write the correct formulas for ionic compounds and for binary compounds like phosphorus trichloride and so forth. And you have to balance these reactants and products together so that you get the correct stoichiometric ratio. In redox reactions, make sure you're also balancing the charge and or the number of electrons being gained and lost, not just the atoms and the mass. Now, in step number two, we begin a process of following a roadmap. And so what's going to happen, the way I like to set them up, and maybe this is the way you were taught it, I would put my number of grams, 1.45 grams, I like to put it above my reactant, and my process is I'm going to convert this to moles. And since my goal in this reaction is to calculate, let's say, how many moles and how many grams of phosphorus trichloride I'm going to create, I'm going to have to convert those moles into moles of phosphorus trichloride, and then I'm going to have to convert that back to grams. That could be one of the problems I'm asked to solve. Or, for example, I could be asked to go from grams of the phosphorus compound to moles of chlorine and then to grams of chlorine. Or, for that matter, even liters of chlorine if I know the conditions, whether you're at STP or not. Or another thing I could have been done is I could have been given the chlorine, and I could have, say, grams of chlorine to moles. I'd get the same answers before, but then go from moles to grams of phosphorus trichloride. And I could reverse all of these processes. In every one of these processes, I could have started off with the phosphorus trichloride and gone the other way. All the way through. And that's what they're doing here. So I call this my roadmap. And this roadmap, when I set it up using dimensional analysis, keeps me from making mistakes. And the most common mistake that is made is to not use the coefficients in the balanced equation, or to have the coefficients when you write your dimensional analysis problem upside down. And this helps to keep me from doing it incorrectly. So in this particular problem, if we're going from grams of phosphorus to, and I'm picking down here, to, let's say, grams of phosphorus trichloride, my dimensional analysis is going to look something like this. I just make a big long line here, and here's where I'm going to put my grams of phosphorus, which happens to be 1.45, and I'm going to, what I'm going to do, I need to get my moles of phosphorus and not my grams of phosphorus. And then once I have my moles of phosphorus, I need to get rid of the moles of phosphorus because I actually want my moles of phosphorus trichloride. And then I need to get rid of my moles of phosphorus trichloride because I actually want grams of phosphorus trichloride. So now when I fill in my places in here, we know we would look up, well, just how many grams of phosphorus are there in a mole of phosphorus. And so I would have to take my, look in the periodic table, or actually, if I'm doing this for homework, I just Google it. And I just say, how many grams in 1 mole of phosphorus. And if I remember this is P4, and the book already did it for me, I have 123.9. So 1 mole of phosphorus is 123.9 grams of phosphorus. And then I want to go from moles of phosphorus to moles of phosphorus trichloride. So I look at my coefficients. And I have a 1 in front of phosphorus. I have a 4 in front of phosphorus chloride. Now I'm going to put my 1 down here because that's what's in front of my phosphorus. And I'm going to put this 4 right there because that's what's in front of phosphorus trichloride. And if you're keeping track, we've gotten rid of my grams of phosphorus. We've now gotten rid of my moles of phosphorus. Now I want to get rid of my moles of phosphorus trichloride because I want grams of phosphorus trichloride. So I could Google that or calculate it on the periodic table, or I'm just going to take the book's word for it right here, 137.3 grams in 1 mole. Now when I go to do my calculation on my calculator, I'm simply going to take 145 times 4 times 137.3, whatever that number was, and then divide it by 123.9, and that's going to get my answer. And hopefully that answer is this answer right there, if I did the math correctly. So you can see your textbook takes this whole page to do what I did right there. I think that's the easiest way to do it. And here in the problem-solving tip, you can see that they do the same thing that I did, grams to moles, and then here's your stoichiometric ratio. This is where you do the 1-to-1 or the 2-to-1 or the 1-to-4 or whatever the coefficients are. That's your stoichiometric ratio, and then you can go back again. And of course, you can reverse the direction as well. You can go this way. And sometimes you just want to stop at moles and not convert it into grams. Sometimes instead of grams, you may want to use a volume. Or maybe you're starting with a volume. And that's where we use what you learn when you study the gas laws and PV equals inert. And how to convert gases from STP to non-STP or back again. So there's all kinds of variations on this basic strategy. Please note that you cannot go straight from grams of reactants to grams of products. You cannot do that directly. Now, if all of your reactants and products were gases, you actually could, because if we were going to convert my gases of reactants into moles, and then my moles of reactants back into gases, I'm using the same number in both cases. I'm using 22.4, which is how many liters are in a mole. And so you can just cancel those out, and you can go straight across if all you have are gases at the same temperature pressure. Now you might remember in first year chemistry we learned how to do ice charts. And ice charts were charts where in the first row we put the amount that we had initially, and it was usually molarity. The molarity we had initially could have been moles. And then we would put the change. We would lose reactants, we would gain products if the reaction's going to the right, and then eventually we would reach equilibrium. And equilibrium would be for those reactions that don't go all the way to the right. Well, you know, in this particular reaction right here, the one we've been looking at, you know it's going to go to the right because you're producing a liquid. And liquids and gases and precipitates make the reaction go to the right, and it's difficult at that particular energy level for the reaction to reverse itself, which is why it goes to the right and goes to completion. So we're not using an ice chart here, strictly speaking. Since we're going to completion, we expect my reactants to go down to zero, and we expect everything to become products. Now, to be honest, I've never used an ice chart for chemical reactions that go to the right. Of course, it's not technically an ice chart. It's an ICF chart, or whatever you want to say that. I've never gone to this trouble to do stoichiometry problems when I know the reaction's going to the right. That would be up to you if you like that element of structure, which is fine. All right, let's take a look at this next example. Here we have a combustion reaction, or we probably should say a oxidation reaction, because this can take place slowly and gradually. And we have glucose right here, a simple sugar. And remember, a table sugar is a dimer. You take two simple sugars, fructose and glucose, and connect them together to get sucrose. So a lot of you have a lot more sugar in your diet probably than fructose, or glucose. But in any case, when we take this food, this element of food, and we breathe in oxygen, our bodies will digest that, and so your whole digestive system is where this arrow is, and there's thousands of chemical reactions, a couple thousand, regulated by a couple thousand enzymes where that arrow is, and then out the end of the reaction comes the carbon dioxide, which we exhale, and the water, which we also exhale or perspire or urinate out. And of course we get energy. So in this digestion process, the goal is to get energy. So this is an exothermic reaction. Now, in this particular reaction, we are given 25 grams of glucose. So we have 25 grams right there, 3 significant digits, which is pretty common. And our goal is going to be defined in this example, I think. Yes, down here, our goal is to find the mass of oxygen. So I'll put a question mark there for the mass of oxygen. So we need to go from grams to moles, moles to moles, and then from moles back to grams. It's a 3-step process. I call it a waltz, my 3-step mathematical process. And down here, of course, we have a 1:6 ratio. So we're going to expect to multiply by 6 in the process. So what your book does then is here's step 1, which is right there. And then step 2 is the stoichiometric part, which is right there. And then step 3 is where we go back to my grams of oxygen, which is right there. And then you can also do carbon dioxide on the other side of the reaction. You can do water on the other side of the reaction. And when you find the masses of oxygen and carbon dioxide in water, you will find that if you add up the masses of your reactants, it will equal the mass masses of the products. And again, I would set up the roadmap like you saw there, and then I would use the stoichiometry. Draw your line. You're going to have a 3-step process. You're going to go from grams of glucose. I'm going to use the letter, well, I'll spell it GLU for glucose. And we need to go to moles of glucose. And then we want our moles of glucose to cancel out, because what we really want is moles of oxygen. And then we want our moles of oxygen to cancel out. So I'll put it on the other above, or I either put it below or above, whatever it takes to get it to cancel. We want our moles of glucose to cancel. Another example where setting up my roadmap and doing the dimensional analysis has helped me out. And I want my grams of glucose right here. And so you can see my moles of grams to moles. I made another mistake, didn't I? I did this backwards. So let's go ahead and erase there and erase there. And there we go. Let's do this again. My grams of glucose to mole, and then my moles of glucose to moles of oxygen. And so now my moles of glucose cancel. And let's see. Oh, I messed this whole thing up. I'm going to erase the whole thing and start it over. Sorry about that. That's why I do dimensional analysis. So here it is, my 3 steps. I'm beginning with my grams of glucose. And I want moles of oxygen instead of mole. Let's see, we have our grams. I want moles of glucose instead of grams of glucose. And then once I get my grams of glucose to cancel, I want my moles of glucose to cancel, because I want moles of oxygen. And that gets that to cancel, and then I'm going to want my grams of oxygen and not my moles of oxygen, which gets that to cancel. There we go. So even experienced so-called experts really depend on the format and the structure of dimensional analysis to keep you straight. And let's come over to the next page. Reactions in which one reactant is present in limited supply. This is way more common. It would be very, very unlikely that in the real world or on a math problem you would be given exactly the right amount of masses of products so that you have no leftover reactants at all. Somebody is rigging the game. If that were the case, there would be some intelligent design in the background. So when we do limiting reactants, the way that I like to do this is, let's suppose that I have 100 grams of aluminum and 100 grams of oxygen, just to make up some numbers, not the ones used in the text. And I want to know which element am I going to use up first. Well, I'm going to go from grams to moles of aluminum, and then from moles of aluminum to my aluminum oxide. And I don't have to go any further, and see what that number is. And then I'm going to do the same thing with my grams of oxygen, and go to my moles of oxygen, and then go to my moles of aluminum, and see how many moles of aluminum the oxygen can make. And whichever one produces the smallest amount the smallest number of moles of aluminum oxide, that is the limiting reactant. If I run out of 100 grams of oxygen first, that's my limiting reactant. If I run out of 100 grams of aluminum first, and it gives me the smallest number of moles of product, then that's my limiting reactant. And notice that because I don't have a 1-to-1-to-1 ratio, because my reactants are not in a 1-to-1 ratio, I need to remember that this is going to be a 4-to-2 ratio here, and this is going to be a 3-to-2 ratio. So you can't always assume, if the mass of each of your reactants are different, that the reactant with the smallest mass is your limiting reactant. That would not always be true, because it all depends upon that stoichiometric ratio. So if we're going to do a calculation, here we're using the oxidation of ammonia to make nitrogen monoxide and water. You can see this reaction is going to go to the right, and you're given 750 grams of each. And so what I would do is I would set up two road maps, 2 moles, and then I would pick a product. Doesn't matter which product I pick. I could read the problem, and if the problem says we're going to be looking at nitrogen monoxide predominantly, then I'll just figure I may have to do this math anyway. So I'm just going to go from moles of ammonia to moles of nitrogen monoxide. And then I'm going to take my 750 grams of oxygen. Let's use a different color. Convert that into moles. And that goes to moles of nitrogen monoxide. I'm going to see which one produces the smallest number of moles of nitrogen monoxide. And whichever one produces the smallest amount, that becomes my limiting reactant. And again, I need to pay it. I can't just look at my original masses, which in this case they're both the same, so I wouldn't be able to use it anyway. But you have to actually convert them into moles, and then you've got to pay attention to the molar ratio. Here you have a 5-to-4 ratio, which is going to step down the number of moles of nitrogen oxide. And then in the case of my ammonia, we have a 1-to-1 ratio. So my moles of ammonia will be the same as my moles of nitrogen monoxide. And here's where your book takes an entire page to do what I was just talking about. So they took their 750 grams of ammonia, 750 grams of oxygen, converted them both into moles, and the oxygen is your limiting reactant. LR for limiting reactant. That's what you're going to run out of first. And by implication, that means there's going to be an excess of ammonia that will not be fully reacted. That will be left over when all is said and done. So I'm going to use my limiting reactant down here to calculate my grams of nitrogen monoxide when I do my stoichiometry. I can also calculate the mass of excess reactant because I can take my moles of oxygen, which is my limiting reactant, and this is my limiting reactant here. I can take my moles of oxygen, and I can find out how many moles of ammonia are required. And since I started with this many moles of ammonia, but the stoichiometry says I only need that many, I can just subtract to get my moles of ammonia in excess and then convert it into grams. And again, I'm not going to bother with a chart like this. I think that's pretty straightforward. In this problem, you're given 365 grams of carbon monoxide, 65 grams of hydrogen, and the temptation is to think, oh, I'm going to run out of hydrogen first because it's the smallest amount. It has the smallest mass, and that would be a mistake. When you have so much more grams of carbon monoxide than you do of the other reactant, it might be a lucky guess. It might work out more times than not, but it would be a guess, an assumption. You have to go through the process to see which one is the limiting reactant. So again, you're going to follow these steps in this strategy. You're going to calculate the amounts of each reactant in terms of moles, remembering to pay attention to the stoichiometric ratio. That's what they do here. And then you're going to use your limiting reactant to guide your calculations through the rest of the problem. And I'm not going to work that out here. You can see here's where they're finding the moles of each. So the carbon monoxide is my limiting reactant. We're going to have hydrogen gas in excess. So I use my limiting reactant both to find out my grams of methanol. This is an alcohol. Remember, you got the hydroxyl group there. And so you're going to have one carbon is where you get the prefix meth. Here's my hydroxyl. This is the simplest member of the alcohol family, if you remember your organic chemistry. And then in order to find out my excess of hydrogen, I'm going to find out my mass of hydrogen that's going to be used up. And then I can say the amount that I started with minus the amount I used. And here's my excess right here. And I'm not going to talk about moles of reaction and limiting reactants because it's a review of everything that I've just said. Let's talk quickly about percentage yield. Now, no chemical reaction in the real world, and I'm thinking industrial purposes especially, is going to be 100% efficient, meaning that you're going to do this reaction and you're going to produce exactly the amount of product as your theoretical calculations, your mathematics, your stoichiometry would suggest that you could produce. So there's a difference between the theoretical, which is the result of your mathematics, and the actual. Because nothing is 100% efficient. And that's especially true the more complicated the chemical technique is. So your percentage yield is you put your actual and you divide by the theoretical. It's the same way that teachers grade tests. Your grade on the test, let's say a test is worth 50 points. Theoretically, you should get a 50, but let's say you only get a 43. That's your actual score, 43 out of 50. And this gives you, of course, a 0.86. And then when you multiply by 100%, it means your grade is an 86%. We do this kind of percentage all the time in many, many, many branches of science. The actual goes in the numerator, the theoretical in the denominator. And so when you go through the stoichiometry and you find the theoretical amount of aspirin, and then let's say when you actually do the experiment and you mass your product, you only get 6.26 grams of aspirin. I hope you don't get a headache because you're wondering what happened here. It just means that your process, whatever process you used to synthesize aspirin, was 33% efficient. It created a 33% yield. And now somebody else needs to come along, maybe your competition in the industry, or maybe in the laboratory you say, well, this isn't going to cut it. We need a better way to synthesize aspirin. So you get creative, you do more experiments, and you see if you can increase the percentage yield. Now, in the real world, in the world of competition and the good kind of capitalism, where you have investors who invest their capital in your company and in your stocks and in your industry and in your salaries, they're trying to get you to improve the percentage yield. And in the process, if you can increase your percentage yield, let's say to 50%, that gives you an advantage over the competition. It also means you're going to have less waste, which means that it's better for the environment. And it also means that your product is going to cost less for the consumer. all of those things are good. And competition in a healthy environment with the right kind of oversight by the government generates these economies and these efficiencies that are good also good for the environment. Now somebody else, another company might come along and they may come up with an invention or a different process, and then they're going to, let's say they're going to be 65% efficient. Well, now they're going to begin to corner the market. Customers are going to begin to do business with them, let's say, and now you've got to improve your game. You've got to step it up. And that's why companies always have research departments, because they want to improve their efficiency. And hopefully now you can see how economy, as well as environmental ecology and concerns, and the right kinds of competition, which involves creativity, which involves limited mandates by the government. For example, when the government steps in and says, you have to sell your product at this price, whether you like it or not, well, you're not going to try to be more efficient, to lower, make it any better or to improve it. You're going to have to sell it at a certain price, and you may go out of business as a result, or the product is never going to get cheaper for the consumer. It's a little bit of an overstatement, but that is exactly what happens when you have too much government regulation. So we're going to stop there with that lesson in economics, I should say, and politics and science.